Hi everyone. In this video I'm going to demonstrate binary logistic regression using Stata, and throughout this demonstration I'm mainly going to be walking you through syntax for how to perform various analyses. Now I do want to mention that underneath the video description you will find a link to the Stata data file that I'm working from, so you can download the data to follow along. I'm also going to include a link to a do file that contains all of the code that I will be covering in this video, and probably code that I'm not going to be covering. And then I will additionally include a link to a PowerPoint presentation that I put together on the topic so that you can gain a better perspective on how to make sense out of various results that we generate. So this video is mainly designed to serve as a walkthrough of the code and some of the basics of logistic regression, but the PowerPoint is designed to give you a much deeper dive on various aspects of the analyses and interpretation of the results. So be sure to download those files to follow along with the presentation. So the data set that we are working from, this is actually some simulated student data that I put together, and basically when we take a look at the data set, you'll find that we have a number of variables in here. What we're going to be doing is predicting the likelihood of a student passing a test as a function of several variables. So we're actually going to run two logistic regression analyses. The first one, we're going to regress this pass variable onto anxiety, mastery goals, and student interest. And then the second analysis, we're going to add in a factor variable, which is this variable right here, income level. So the pass variable, which is our dependent variable, is coded 0 for did not pass a test and 1 for did pass the test. So you can see down here we have pass the test and we have did not pass the test right there. So next, what I want to briefly show you then is the do file that contains the code. So again, you can download this do file at the link that's provided underneath the video description. So this is it, and like I said, I've written a lot of code in here, and the intent of the video is just to kind of walk you through the code so that you better understand how to use it in order to efficiently run your analyses in Stata. I know there is a menu system in there that's pretty easy to use, but sometimes it gets a little bit more clunky, and so knowing a little bit of the code can be very helpful in expediting things. And also, if you can write it into a do file, then you can batch run many aspects of your analyses. So it's a really nice feature of Stata. So if you're not familiar with it though, basically to open the do file, you just go to the box for or icon for new do file editor, and that will open up a box, and that's where you would write your code in. So I'm going to go back to my do file code and begin walking you through it. So first off, what we're going to do with our first model is to run a logistic regression with our pass variable serving as our binary outcome variable, and anxiety, mastery, and interest serving as predictor variables. And one thing you need to keep in mind is that your dependent variable, or your binary dependent variable in your logistic regression, should be coded 0 and 1, because Stata is going to recognize a 0 as a failure, so to speak. Basically, that's reflecting a case that does not fall within the target outcome, and then a 1 is going to indicate a success, meaning that the case falls within or falls in the target outcome group. So when I use the term success and failure, I don't mean it in terms of good or bad, only to indicate that Stata is going to recognize those codes as reflecting a case that's falling into the target outcome group or the non-target outcome group. So just kind of keep that in mind when you're running your analyses. If you need to recode your dependent variable before you run your analysis into 0 and 1, be sure to do that. So at any rate, the function that we're going to be using is logit right here, and so we're basically going to lay this out very similar to a standard linear regression in Stata. So we're using logit as our command, followed by the name of our dependent variable, which is pass, followed by the names of our independent variables right here. So once you've typed all of this in, you can highlight it and click on the execute selection button, and you can see that it runs. And also, really quickly, I do want to mention too that you'll notice that the green lines, those are just basically comment lines. I'm starting those with an asterisk. So if you start a line with an asterisk, then Stata is going to recognize everything that follows as a comment. So I try to kind of give you comments throughout this do file. So you'll notice in terms of our output, what we have is right here we have our likelihood ratio chi-square. This is basically testing whether our model containing the full set of predictors represents a significant improvement in fit relative to a null or intercept only model. So you can see right here we have the p-value that's given, and so we would infer then that our model that contains our predictors does represent a significant improvement in fit over a null model. You can see this pseudo R square right here. This is actually McFadden's pseudo R square, and this gives you a basic indication of model fit as well. Just keep in mind that when we talk about pseudo R square values, these are rough analogies to the R square value that we are familiar with in the context of linear regression. And so you shouldn't interpret it as an indicator of the proportion of variation accounted for in the dependent variable. But you could interpret it as the percentage or proportion of improvement in fit over a null model. And I do kind of break that down in terms of the computations and so forth in the PowerPoint, so you can see that a little bit more clearly. So looking at our regression coefficients right here, these are the unstandardized regression slopes. These are the standard errors, z-values, and the p-values for testing the regression slope. So you'll notice that anxiety has a negative regression slope, whereas mastery and interest both have positive regression slopes. And just kind of keep in mind that what we're looking at when we're talking about the regression slopes, what we're talking about is the predicted change in logits or predicted logits per unit increase on the predictor variable. So I know that logits are kind of unfamiliar territory for many people, and I do break that down again in the PowerPoint presentation, but you could roughly think about a negative value as signifying that as we move from lower to higher scores on the anxiety variable, the predicted probability of the student passing the test would be decreasing. For positive coefficients such as for mastery and for interest right here, you can see that basically that would indicate that as we move from lower to higher scores on mastery or interest in that case, the predicted probability of passing is increasing. So just keep in mind that passing is the target outcome and not passing is the non-target outcome. So you can see then that we have two of those predictors are statistically significant, whereas the third one is not. Now there are some other indices that we might wish to obtain or test. We have the Hosmer-Limashow goodness of fit test right here. That is given as ESTAT, so we're using the ESTAT post-estimation command, followed by GOF, comma, and then you can see right here it says group and inside parenthesis 10. So when we highlight this and run it, we get the Hosmer-Limashow goodness of fit test. And what we're looking for with this test is non-significant. So whereas the previous likelihood ratio chi-square test up here is indicating significance, and that's regarded as an indicator of good fit, what we're looking for with the Hosmer-Limashow test is non-significance. And you can see right here the p-value is 0.9776. So this is another indicator that we have at least acceptable fitting model. We can also use the ESTAT post-estimation command to generate a table reflecting classification accuracy. So you can see right here that I've typed in classification, comma, and then all. So when I highlight this and run it, I get this table, and this gives me information regarding the sensitivity and specificity of the model, as well as the positive predictive value and the negative predictive value. So taking a look at our table right here, you can see what it says true. These are the observed outcomes. So this outcome right here, this is reflecting those individuals who were observed to pass. Okay, so we had 245 students who passed the test, and we had 180 students who did not pass the test. So you can see that little tilde D right there. And so with respect to the sensitivity of the model, this 80.82, that's calculated pretty easily by taking the number of students who passed that were correctly classified to pass, which was 198, and dividing it by the ratio of, or dividing it by the total number of students who were observed to pass, which is the 245 right there. So we had 80.8% of the students who were observed to pass were predicted by the model to pass. With respect to the specificity of the model, now we're looking at the second column over here. And so right here we see that of the 180 students who were predicted not to pass, we had 71 that were correctly classified as are predicted by the model to not pass. So if we take 71 and we divide that by 180, we end up with 39.44%. So that's just a really quick overview of using this particular table. Again, in the PowerPoint, I actually go through unpacking the sensitivity, specificity, and then I also cover the positive predictive value and negative predictive values. Okay, so now we're going to transition, and we're going to rerun the analysis, but in this case we're going to request odds ratios instead of the unstandardized regression slopes. So the way that we do this is we rerun the analysis as we had before, but now we're going to add in an option. You'll notice that we follow the last predictor with a comma right here and then type in OR, and that's for odds ratio. So when I highlight this and click on execute selection, you can see now I have in my table a column of odds ratios, and then I also have a 95% confidence interval for those odds ratios. And so in terms of interpretation, again, I kind of unpack this in a lot more detail in the PowerPoint, but looking at the odds ratio for the anxiety variable, it's 0.922. So what that means is that for every 1 unit increase on anxiety, the predicted odds of a student passing are multiplied by a factor of 0.922, and that actually means then because this number is less than 1, that means that the odds are decreasing. With respect to the mastery predictor, we have an odds ratio of 1.1, so that means that for every 1 unit increase on the mastery predictor, the odds are multiplied by 1.1, and that's because that number is greater than 1, that signifies that the odds of passing are increasing. So the same general logic would apply with respect to the interest variable right here. Okay, so it may also be of interest to you to generate predicted probabilities for each case that a case would fall into the target group. Basically, the student is the probability of a student passing based on our model. So you can do that by using the predict command, and you'll notice right here I'm just using P, and so if I highlight this and I click on the execute selection button, a new variable has been generated in the data set that represents the predicted probabilities. And if you wanted to generate predicted group memberships based on those predicted probabilities, you can do that very easily in the following way. You'll notice that I have the generate command, and I'm creating a new variable. I'm just going to call this PRGP. You'll notice it says equals, and then there's a period at the end. So if I click on that, it's going to create this new variable, but there's no values in it. So I'm going to replace the missing values, if you will, in the following way. So I'm going to use the replace command followed by prgp set equal to 0, and then it says if, and then inside the parenthesis p is less than 0.50. So remember, the p is referencing this variable that's been created up here, the probabilities. So if the predicted probability of a case falling into group 1 is less than 0.50, then that's going to be replaced with a value of 0 on this new variable. And then if the probability is equal to or greater than 0.50, which is reflected right here, then we're going to have a value of 1 that is going to be included in that group membership variable. So that's basically all it is to it. So if I highlight these, I've already generated the PRGP variable. Now I'm going to do the replacement, and so now we have that done. So if you go under Data Editor right here and kind of scroll over a bit, you'll see we have the predicted probabilities and the predicted group memberships. Okay, so now let's say that we want to generate some regression diagnostics. Once again, a lot of this is unpacked in a lot more detail in the PowerPoint, but I am going to walk you through the code, just showing you how it's created. So first off, let's say that I want to generate unstandardized residuals, and that's going to be the difference between observed group membership and the predicted probability that a student has passed, basically where y is equal to 1 instead of 0. So to do that, we can use the generate command right here, and I'm creating a new variable right here. I'm just going to call it UNRES for unstandardized residual. I'm going to set that equal to pass, which is the name of the dependent variable, our binary dependent variable, minus p, which is the predicted probability that we've generated up here. So if I highlight this and run it, I now have a variable in my data set reflecting the unstandardized residuals. The next thing I'm going to generate are Pearson's residuals, and these are pretty useful for identifying potential outliers. So in this case, I'm going to use the predict command right here, and right here I'm just going to give it a name. I'm calling it Pearson resid right there. I have a comma, and then we're generating residuals right here. Okay, so there we go. And sorry, I just had a little bit of an error there, but okay, so now we've got our Pearson residuals. If we want to generate leverage or case-wise leverage values, we can use the predict command again, followed by a name. I'm just going to call it leverage, followed by a comma, and then hat. Okay, so when I highlight this and run it, that variable is now created. So let's just take a quick look at these variables that I'm creating for the data set. So if I go over here and scroll over, you can see we have the unstandardized residuals, we have the Pearson residuals right here, and then we have leverage values that are given right there. And I'll go ahead and open up the do file and just kind of mention that another thing that we might want to ask for are DF betas, and are basically the standardized DF beta for our predictor variables. And the DF betas are useful when it comes to identifying cases that may be particularly influential on the individual regression slopes. So right here I'm using a command called LDF beta, and you'll notice that I'm following it with the names of my three predictor variables: anxiety, mastery, and interest. Now it's extremely important to keep in mind that the LDF beta function or command is basically associated with a package that you have to download and install before you can use it. And that package, unsurprisingly, is named LDF beta. So just in the interest of kind of demonstrating everything right here, what I'm going to do is I'm going to kind of minimize this and click out of here, and I'm going to go down to the command line and I'll type in search LDF beta, and when I click enter, now you can see that we have the LDF beta package right here. You can click on this link, and it'll take you to the site where you can then install it. So if I click on install right here, it's already actually been installed, but that's basically how you can obtain it. So getting back to our analysis then, I'm again going to use the command LDF beta, and then we follow that by anxiety, mastery, and interest. So I'm going to highlight all this and run it, and so now we have 3 new variables that are added to our data set. We have the standardized DF beta for anxiety, for mastery goals, and for interest. Now in the PowerPoint, I cover these different indices, and I provide some demonstrations of thresholds for making judgments regarding these particular indices. I also incorporate a demonstration of generating an index plot for leverage, and you can use the index plot also with respect to the other measures. So the way that I do that in the PowerPoint is I use, first off, I have to obtain case IDs for my observations or for my subjects. So I'm going to use the this gen command right here, followed by case underscore ID. That's going to be the name of a new variable that's created for the data set, followed by equal, and then followed by an underscore n. So when I highlight this and click on execute selection, I now am going to have a new variable in here. This is the case ID variable. Rather than opening up the actual data file, there it is right here. So next I'm going to use the two-way plot function, and inside the parenthesis I have bar. So I'm going to create a bar chart, and then you can see it says leverage followed by a space where we have case ID, so the variable that we are basically generating right here. So when I highlight this and click on execute selection, you can see that I get an index plot for the leverage values. And so looking at this, you can see that it looks like there's at least one case that is demonstrating much greater leverage relative to the others, but we do also have a couple of these cases right here that are exhibiting greater leverage. Just briefly, leverage essentially reflects a potential multivariate outlier with respect to your predictor variables, and cases that are high leverage have the potential for being high in influence. So that's why it matters that we would want to investigate leverage. So there you have it. There's basically just a quick run through of how to generate various regression diagnostics to evaluate our model. We also have one other diagnostic procedure. If we want to generate collinearity diagnostics, you can do that very easily by using the colin command right here. So you'll see I have colin followed by the names of my independent variables. So when I highlight this and click on execute, you can see now I get tolerance values and variance inflation factors, and so these are commonly used to evaluate the presence of multicollinearity among the predictor variables. Okay, so now the last topic that I want to briefly cover is just running a model where we have the income level variable added into the model as a predictor. And so income level is an ordered categorical variable. Basically we have students that are low, medium, or high in income that are represented, and so I want to run the analysis treating that variable as a factor variable. So what we're going to do is we're going to again type in logit followed by the name of our dependent variable, followed by the names of our continuous predictors right here, followed by the name of our factor variable, but we're going to have to use the I dot prefix in relation to that. And what that's going to do is it's going to lead Stata to recognize that variable as a factor variable. So I'm going to highlight all of this and click on execute selection right here. And so now you can see that we have our output. You can see the likelihood ratio chi-square. We have statistical significance. So this model represents a significant improvement in fit over that intercept only model. The McFadden pseudo R-square value is 0.0806. So basically we see about an 8% improvement in fit relative to that intercept only model. You'll notice that our regression slope for anxiety is still negative and statistically significant. For mastery goals, it's positive and statistically significant. And for the interest predictor, that slope is still positive, and also still not statistically significant. You'll next see that we have this income level variable represented in the form of two dummy variables. We have medium income, and that variable is basically coded in such a way where students who are in the medium income group are coded 1 and students in the low and high income groups are coded 0. The high income dummy variable right here is coded such that students in the high group are coded 1 and then students in the other two groups are coded 0. So the regression coefficient that you see for each of these dummy variables represents comparisons between either the medium group and the low income group, or the high group or high income group and the low income group. So that's basically what's going on right here. So you can see that we have significant differences between the medium and low group and the high and low group as well. And because both of those coefficients are positive, what they're essentially signaling is that, first off, students in the medium group are more likely to pass the test than students in the low group, and the same goes for students in the high income group being more likely to pass the test than students in the low income group. And then, as I mentioned above, really all of the same commands are in play. If you want the odds ratios, you can just rerun the analysis by incorporating the OR option. So if I click on this and highlight right here, you can see that now we have our results given in the form of odds ratios. You'll notice that again we can use our EStat GOF comma, then followed by group, and then the 10 inside the parenthesis to generate our Hosmer-Liebeshow goodness of fit test. And then we can also generate our classification statistics as before by using the EStat post estimation command followed by classification, comma, and then all. So that's basically all there is to it in terms of running these analyses. Just so you know, if you wanted to generate that intercept only model, I don't know why anybody really would want to, but if you did, it's very easy. You can just type in the logit command and follow that up with the name of the dependent variable without any other of your predictor variables included. And if you run that analysis right there, you get your intercept only model. So that pretty well wraps up this discussion. Again, I know this is very quick, very blow by blow through each of the commands that I'm covering, but I did want to try to keep this reasonably short video. It's not terribly short, unfortunately, but nevertheless, you can go back and look at the PowerPoint for a deeper dive on interpretation and what different aspects of the output represent. So thank you again for watching, and you guys have a great day.